Hello again, everyone. So the topic of today's webinar is hybrid MPI and OpenMP parallel programming. So my name is Jamie Hu. I'm one of the Sharcnet high-performance technical consultant. So if you'd like to find the slides as well as the sample code, you can find them on Sharcnet systems under my home directory, and then say is 706/hybrid. Okay. So today I plan to briefly talk about the difference between message parsing, the MPI, and the shared memory OpenMP approaches. I assume you have the concept of MPI and OpenMP, and we don't talk about the details of them, certainly. And then we'll talk about why or why not hybrid. And after that, we'll give a simple, straightforward approach to combine both MPI and OpenMP in parallel programming. I will use an example to demo the approach, the concepts I talked about. And then I will also talk about the compile and the execute hybrid code on Sharcnet clusters. So those are not only for the code you wrote or you will write. It's actually some applications that already take these hybrid approaches and will help you in the future if you use some third-party softwares. You will know how to compare it and how to run it correctly on Sharcnet systems. So as for any parallel computations, so before you actually start to run your code, it's always good to understand some basic hardware architectures. So that's the basic for you to run the best your code could be. So this graph gives a simple description of the parallel distributed shared memory architectures. It's the simple computer cluster basics. So the cluster is composed of many nodes. So each node is a shared memory load. So it's usually called coherent SMP node. Now all the CPUs, sometimes we call it processors, or we call it cores, on a given node and can access the memory, address those memory as a global memory. And in the meantime, and all the nodes are connected by a network. So for this process on one node, they only know the data is on the memory. So the CPUs on a different node will not know the memory on another node. So that's the thing when you have data cross-node, and the networking will play a central role for the data communications. So it will need the network communication to move data from one memory location to another memory locations. So this is the trends for any type of cluster. And in the future, maybe the cluster will be bigger and will have more loads. And then each node will have more CPUs or possibly a big chunk of memory. But the concept is always like this type. It's always a hybrid distributed shared memory architecture. So SMP stands for distributed memory communications. It's the standard for distributed memory communications. So message parsing interface is basically a library-based. Any of you, if you have any experience, you will understand the concepts. It provides an explicit means to use message parsing on distributed memory clusters. So it can it specializes in packing and sending data structure or simple or complicated over network. So each processor has a means to access the data sent to it. And at the end, you need to do the synchronization, basically handle explicitly due to the latch of distributed memories. It's basically you do all the data synchronizations in a code, and you do it yourself. On the other hand, OpenMP is a shared memory paradigm. It uses implicit intra-load communications. So it uses efficient utilization of shared memory. And the big feature is it's easy to code. It's basically technically threaded programming, and it's supported by the most major compilers. So the compiler and the system setup will do the major job for you. So the process goes to data because the data will set one copy in a memory, global memory location, and all processors on that load can access to that same copy of data. So communication among threads is implicit. So if you want to, if you would like to compare these two approaches, as we know, and each of them, they have their pros and they have their cons. In the MPI side, well, pure MPI is portable to distributed and shared memory machines. A good MPI code can run any type of multi-core machines. It doesn't matter it's distributed or shared memory. And it scales beyond loads because you want to run your code in a big scale and to use as many CPUs as possible, so you can use CPUs on different loads. So sometimes it can scale very big. And normally when people say there's no data place problem because you handle with the data distribution and synchronization, or in your code, you understand what you have done and where the data is sent to. And then the cons for the MPI, and it's basically because it does explicit communications, so the data communications are handled in the code itself, make it a little bit complicated in the coding side. And the type typically is a high latency, low bandwidth solutions because of the data communication between the CPUs on different nodes will take a little bit latency, a little bit of time. And sometimes it has problems to deal with load balancing issues, and because each CPU and each processor may not get roughly the same type of tasks. So some will finish quick and some may have more job to do or run longer. That will slow down the whole processes, and it will have speed up issues sometimes. On the other hand, OpenMP will basically sort of the advantage of OpenMP is basically the disadvantage of MPI. And OpenMP is easy to implement, and communication mostly is handled by the constructors. And there's some barrier or implicit barrier there. You don't need to worry too much. So it's a low latency, high bandwidth solutions. And the load balancing is an issue as well, but mostly it can be handled by dynamic loading. On the other hand, the disadvantage for the OpenMP because it's only work on shared memory systems, either on shared memory load on cluster or on a shared memory machine. So you cannot run very large, really very large scale, and because it doesn't run on CPU's cross loads. So that limited its usage. And data placement is a problem, and data race is a big issue in OpenMP, because OpenMP or threads will access to the same one copy of the data. So when you read and write data, you will need to deal with the data race issues there. So why hybrid? Well, basically, the simple idea is, we want to employ the best part from both approaches. So MPI makes inter-node communication relatively easy. So cross-load, you want to make as many CPUs, many processors work for your code as possible. So it has many good ways for MPI to handle it. And also, the synchronization cross-loads is an advantage for MPI to handle with all of them. OpenMP, on the other hand, were enough for high performance, relatively straightforward within-load, intra-load threadings. It's basically will speed up the runs on one node, and it will hopefully it will reduce some communication time, the communication so-called data communication time between nodes, for those nodes with one between CPUs, for those CPUs are sitting on one node. So the overall goal is basically to reduce communication needs and the memory consumptions, and or improve load balance. Okay. So the question will come, say, do I really need to use both in one code or not? Well, it's always case by case. Sometimes it works better, and you like to go for it. But if it doesn't work for you, well, there's no need for you to spend time on it. So it may not work well if you say, hey, I list the cases of OpenMP code performance is worse than the pure MP code with one node. So the case, for example, if MPI communication takes lots of time, and when you do the MPI communication, all the threads, other CPUs on the load will be idle. But in this case, where maybe the OpenMP will not perform better than the pure MPI. And the other case is, say, if you have difficulties to deal with data, and you cannot handle the data race problems in OpenMP, and you may not want to add OpenMP to your MPI code. And the other thing is OpenMP itself, when it does synchronizations, there are some sacrifice of the speed. So, for example, when it does critical sessions, or it will slow down the whole processes. So if the critical sessions is heavy for shared variables or something like that, so OpenMP may not perform well. So the basic thing is, in any type of parallel programming, your goal for you is you want to speed up, you want to run your code as fast as possible. So if it's not, well, all the coding efforts will possibly is a waste of your time. So a common approach for hybrid parallel programming, and basically, well, we all know the sequential code, and when you're starting with a parallel code, you better start with, say, MPI first, And then because MPI will give you a full scale, you will have to plan for the algorithm to how to divide your task into pieces, and each task will assign to processors. And then that will be some changes to your algorithm. And then, you can try to add OpenMP into your MPI code. That's the basic approach. That's the approach we'll talk about today. And certainly, you can go the other way around, as long as you use the thread-safe MPI approach. You can actually make MPI calls within parallel regions. So one way is basically the commercial and popular way is you have an MPI code. You try to add OpenMP, and to later the CPUs on one node will run in OpenMP thread in parallelism way, and the other way around is you can try it as well. Okay. So here is basically is a protocol for a hybrid code. So this is basically say, assume we start with MPI. So it's always MPI initial, MPI the rank, the size, and then you will do some MPI communications. Is the what data to which, and then you within your MPI code and some part, and you start OpenMP region, and the OpenMP part, and it follows CPU sitting on one node, and you can do some OpenMP run in a threaded way, in OpenMP way, and after that, and then you come back to MPI communications, and that then your finish is MPI finalized. So this is a prototype, and for the, I think we'll use the next slides to explain how it really runs. Okay, and this is the framework for this type of MPI and OpenMP programming. So here you use MPI will start with MPI run, and you may have multiple CPUs start, and each processor will assume start on one node. So this will be used say one node. This is another node, and so on each node only you run one MPI processors, and those MPI processors will create a team of thread, and let your code to run in the OpenMP fashion. So you have a master processors, for example, and then it will behave as a master thread, and it will fork a team of threads, and basically use multiple CPUs and to run your code. And this is also run in OpenMP multi-thread fashions. And then the other MPI processors will do the same thing on another node. And so the code itself looks like it's MPI code from outside, and with one node, where it looks like it's OpenMP code. Okay. So here we compare the load latch. We can say here, for example, we use 16 CPUs across 4 nodes, and assuming use 4 processors per node. And in MPI, we use 16 CPUs across 4 nodes. Is actually each CPU will run one MPI process. So that means we have 4 independent MPI processors per node. So with MPI and OpenMP, we still use 16 CPUs work for your code. And in this case, on each node, we only has actually start one MPI process. And this one MPI process will open, say, 4 threads. So on one node will be one MPI process and 4 threads to work for your code. Okay, so that's the basic concept we want to cover to introduce to you. Where you have MPI, you understand MPI, and you understand MP, OpenMP, you know how does the code run on the systems. And then it's basically the simple hybrid concept for the combine of MPI and OpenMP. Now, next I will use a simple example to demo to show you how the code looks like. Okay. So the example used is basically to calculate pi and take the numerical approach. Numerical integration is something like you basically do the integral cross from you do this type of calculations. It's basically you calculate area under this diagram, right? And then you can always transfer this type of integrations to be a sum of this type and then you basically you can you can compute each part of it, and then you can add them all together. So the more you cut it and you divide your task, the better your result will be. So calculate this approach to calculate pi and in sequential code is very simple. And you have one node. In this case, in program this case, you have one for loop, and basically you get it done. And the code is as simple as some type like this. So if you want to go to MPI solution, it's not complicated at all. And it's basically here you want each MPI processor to do part of the work, and the other MPI processor to do another part of work. And eventually you add all the sum together, and you will get the whole part. So the idea is something like that. In OpenMP's case, where you want each part will be done by one thread, and the other part will be done by another thread. Again, you use multiple CPUs or multiple threads to do the whole job, and then to speed up your calculations. So, yeah, different approach, but they all basically achieve the parallel calculation that goal, right? So the API code, the simple code something looks like this, and you the number of steps, or basically number of bins you want to calculate it, and then you have a few variables to define. And for example, you have your my ID, and each MPI process will have ID. The rest from 0 to the number of processor, number of CPUs you use -1, and you will want to know how many in total. And then where you some other necessary variables for your problem. And MPI will start with MPI initial, and then this is basically get the size is how many processors I will use for my MPI code. And then this is always called for who am I, and my number is from 0 or 1 or whatever number. So these two numbers are important for MPI to communicate which processor will send the data to what or get the data to what, right? The same thing will for the OpenMP. They have the total number of threads and the thread ID. So those are all important. And once you have that, you basically run this loop. You can see the index of the loop. So it will start with my ID, and then it will run number of threads, and then the total number of process I use. And then in this case, this is the simplest approach. So you know each will work on part of it. And in this case, it's simple. You take one piece at a time, one chunk at a time, and it all run. The next time it will take the next, right? And then each will calculate the sum, and then at the end, the simple MPI reduce will add all the sum together. And you can print out the results, whatever you want to do, right? So because we know the ID and we know the total number of processes, so we can simply change the sequential code from the index to this type of index, where MPI is a simple way to go in this case. Now we can say the OpenMP is the same approach, and same idea. And in this case, well, the same thing. Some variables you define. You can say this program OpenMP is started for OpenMP part. When you compare the code, the compiler will know this part will do in parallel multi-thread. So it's a parallel for loop and a parallel for loop. And here use some where the OpenMP there is a reduction or do the sum or something. You can schedule what type of schedule to run, and then you basically run the step and the index there, and you basically will do this type of sum, or basically will add all together. And then finally you want all the steps add the sum together, and then you can print out it, right? So this is a separate solution for MPI and OpenMP. Now we want to combine them together. The concept here is quite straightforward. So in this case, for example, we can let each MPI processes take a part of the task, and they basically one MPI, each MPI process integrates over a range of the weight. So for example, here in this part. And with this MPI process, we'll create a team of thread, and where each thread will work on part of this part, right? A part of this part. In the fourth case, for example, we have rank 0, rank 1, we may have more, and then we have each thread will work on this, a large thread will work on this part, and blah blah blah. It's something like that. So we transfer, we change this concept to real code. The code will look something like this. So in this code, in the both, when we have an MPI code, we know it's a library based for MPI. You need to include MPI.h header file. And the OpenMP is a compiler constructive and compiler based. However, it still has a library course as well. And so it comes with OMP.h header file as well. And then the same thing, you can specify how many beans to cut your task, and then you can specify how many threads per processor to use. Well, you can hard-code it, or you don't need to hard-code it. It's an option. And then here, variable combinations basically is for both of them. This is part is for total number of thread of MPI processes, and each MPI processor will have its own ID, and you want to know how many threads to use, and each thread's the ID as well, and the number of beans. and this something is the same. So the code will also start with MPI code, and MPI the same course here. And then you want to specify, well, as we said, the total number of bins, well, you divide the size to be the number of your MPI processes. And then the major part is, so with the MPI processes, you call OpenMPI, OpenMPI regions. And the OpenMPI regions here, the number of threads and each thread's IDs. So the trick will be here is the index. See, in this type of index, where each will start with is a combine of both IDs. So this is the MPI ID, this is the thread ID, and then you have each the number of threads to iterate, and then how many in totals to change for it, right? And once you have that, and each thread will add the sum together, or get the whole numbers to run on. It basically belongs to one MPI processes. It's the sum produced by all the threads on one node. And then beyond that, after that, you can do MPI, come back to the MPI core, MPI reduce, or add all the results together. And then that's it. That's the end of it. So this is basically take the simpler approach and to demo these concepts. Okay. So once we have the code and whatever you wrote you wrote yourself, or you have a sort of hybrid code from online or somewhere else, or you need to compile it correctly on systems. On Sharcnet, and we have the compiler commands or something like this. So for say code, the MPI+CC is to compile pure MPI code. So MPI+CC, and then this is say your binary name. You have say the source code. For the OpenMP code, a pure OpenMP code, where you use the simple CC stands for to compare C code. You need to add the dash OpenMP flag to your compiler to enable the OpenMP part, and then your binary name and your source code. For the hybrid MPI OpenMP, so you need to use the MPI compiler. So MPI+CC, you need to invoke the dash OpenMP, and then this is your final binary name, and this is source code. And then you start to run your code. Well, for example, I run a pure MPI code. I have to submit job to MPI queue, and for example, ask for 8 CPUs. And then this is basically, you can add it, you don't need to, and it's for my demo purpose. So for example, this is basically you say on each processor I want to use 4 CPUs. And this runtime and your log file, these 2 options are mandatory. And then is your binary code. For the sequential, for the OpenMP code, you need to submit job to the threaded queue. And then you need to say I use 8 CPUs. It's basically each CPU will work as a thread for you. For the hybrid code, where basically it also says API code, submit job to the API queue, and then in this case the total number of CPUs we're asking is 8. Let's give you 8 CPUs. In this case, where you say each or on each node will have one, basically it's one MPI processors, and then the TPP is basically where each processor will open 4 threads. And then the other is something like that. Okay, you can you basically compare your code and you run your code, and hopefully it runs correct for you. So I have the sample code is on my home directory, and you can find them. So you can check the results. Something looks like this, and this is the results I ran previously. And So here our MPI, if we do the SQ sub as we done before, it's basically since we're using 8 CPUs, we're doing the calculation will give the results here. The OpenMP, something like that, the hybrid, and actual proofs. Well, in this case, we're use 2, is basically is 8, and each 4 threads is basically use 2 loads. So MPI process is only 2, and each will use 4 threads. And you can say each processes the sum is how much, and the total the results, something like that. So I want to try to show a little bit demo for this. And so here if we go to the directory here, and you can find the slides, the PowerPoint slides is there. And the sample code is on the here. So you can see, I will show you, the first one is the OpenMP, pure OpenMP code to calculate the pi. So here is basically is a sample code as I showed on the slide. So it's basically is a one loop to run through the slides and or get that part. Okay, so I will keep it back up there. So if I want to compare my OpenMP code, you compare use the flag dash OpenMP, and then, for example, give a name. Hopefully this works. Now I have this binary code there, right? Now I can do the same thing for the MPI code. So if we compare MPI code, MPI CC-O MPI-C. So that's the MPI code. So the name is newly compiled. And then we want to do a hybrid code. So what we need to do is MPI-CC-OpenMP. Hopefully it will work for me today. Seems to be fine. All right. So I'll try to submit a job for the pure 3D job. I use 4. I use 8. I give it one name there. So this is the way to run a pure 3D job. So I use the default memory to do that. So the job is queued there. I don't know how long it will need to wait. Hopefully will not be that long. And then if I run a pure 3D job, MPI job, basically you just need to do whatever but I use. I don't need to use any imitations there. So the job is running right now. It's good. Now finally, we want to do the submit the hybrid code. So I can use that one I used before. I have a README file there you can check. So here basically so this basically submit job to the MPI queue use 8 CPUs, and on each node will start one MPI process, and each process will start 4 threads. That's the way for you to run hybrid code. And MPI is done straight for so long. Okay, we can check the output now. So this is my original run. This is the new run. So here is the MPI results. So the MPI results basically use 8 processors, and this is the roughly results. The time to calculate it, and the other one is waiting there. Okay, the hybrid is done as well with. It's all rated, I think. So this is the result for the hybrid. So you can see here the code is basically use 2 MPI processors. Each will use 4 threads, and the process 1 will calculate that big one, and the process 2 calculate that small one. So the total MPI processors are 2. Actually, you got 8 processors to work for you as well, and this is the final results. Somehow the OpenMP doesn't work well today. It still keep running there. Anyway, this was the old results for the OpenMP code. Okay, so this short demo is basically show you. So you know how to program in MPI, and then you understand the concepts of OpenMP. You know the framework to combine both of them, and 2 of them, and then you go to your approach for hybrid coding. This is a simple example, and basically give you that concepts and for the approach. Okay, so we come back to the. So last one will be the summary. So, you know, computer systems is basically lossless all clusters. Is a hybrid architectures or allow you to actually run hybrid fashions, multiple core. For multiple cores on one node to run in an OpenMP way, and for your MPI jobs to cross multiple nodes. And whether or not and it makes sense to you, finally it depends on the speed. And when a hybrid code performs better than the MPI code, and then you certainly you would like to try to hybrid code. If not, you don't go for it. And nowadays, there's a more positive experience, and many applications actually take this type of approaches, and it makes sense. And if it makes sense, well, you would like to try. Okay. So the reference, there's some good tutorials online. If you're interested in, you can find some very good real applications for the hybrid approach. Okay, that's all for today. Thank you.